The last speaker of my session is Csaba Csaki from Cornell.
Thank you very much, and it's a great pleasure to be here to celebrate Hiroshi's birthday. And many of you may be wondering, what does a phenomenologist do here at this meeting? And of course, this is one of the explanations. Yes, so this was one of the papers that we wrote. That was one of the first phenomenological applications of the ADS-CFT correspondence. We were trying to see, if it has any predictions for real-world QCD. And when I was looking at this a few days ago, I also noticed this is JHEP01. So this was in the very first volume of JHEP. So that's another nice one. I was really trying to find some pictures of Hiroshi from that period, but I couldn't find any. I did find one picture that has many of his collaborators from Berkeley at the time. So since several of them are here, I decided to actually put it up, and we'll see, we were quite a bit younger, and you can see our first speaker here, and then a speaker from tomorrow, and then there's me, there's Kentaro. I guess, Hiroshi wasn't, in his wave function or his spectral density basketball doesn't show up with a big, with a big factor. Okay. Now, another place where we have intersected, and that's something that hasn't been mentioned about Hiroshi yet, is that he has a fourth life also, besides the first three, which is the Aspen Center for Physics. And he has, of course, been instrumental over the last several decades. He has served as the president, and now he's the chair of the board. And that's another place where we're intersecting. And I took this picture of him, and I really love this sequence because it will sequentially go out. You see here, you can see where it is. It's one of the barbecues, and now you can actually see what is happening. Okay, and I have a few more Aspen pictures. So this was actually somewhere out here during one of the. It's related to Aspen. It was one of the admissions meetings. Now I guess we are allowed to say yes. And this is last summer at the retirement of Patty. Hiroshi was representing the center. And this was at the 60th birthday of the center. All right, very good. So since I'm a phenomenologist, I try to pick a subject for this talk that is hopefully actually interesting for most of you in this audience, which is related to the scattering of electrically and magnetically charged objects with each other. So I will give you first a quick introduction of why the electric pole system is pretty weird. And then I will try to give you, this will be the key part of the talk, how to sort of find new type of multiparticle representations of the Poincare group. And you will see that there's a new concept which is called pairwise little group and pairwise helicity that is actually going to be emerging from this. And we will then, take this more abstract group theory discussion and try to really translate it into something that is useful for those who like to write down scattering amplitudes. So we will introduce the sort of, spinor-helicity variable for this new kind of little group, which we'll call this pairwise spinor-helicity variable. And then we'll start showing, how to build actual scattering amplitudes. And I'll talk about, maybe if I have time, for the scattering of gap monopoles. And at the very end, I probably won't have much time for this, is how this whole thing actually shows up from the dynamics. What's the dynamics that is being captured by this group theory? All right, very good. So the weird properties of the monopole charge system, they mostly go back to this famous formula that was known already by J.J. Thomson, and I was told even before him, that if you just go ahead and calculate the angular momentum of the electromagnetic field that is generated when you have an electric and the magnetic charge separated some distance from each other, then actually this angular momentum doesn't depend on the distance between the electrically and the magnetically charged object. It only depends on the relative position, on the relative direction of the charge to the monopole. So this is a unit vector here pointing from the monopole to the charge. Okay, so if Thomson knew about quantum mechanics, he could have already, just from this, derive the Dirac quantization condition. Since, you know, there's an angular momentum here, its angular momentum should be, you know, quantized. And, you know, if he knew about that, he would have noticed that, you know, E times G has to be, you know, a half integer. Of course, he didn't know about it, so he had to wait another 30 years for Dirac. This is, of course, also applying for dyons, and you know, you have the famous Zwanziger-Schwinger condition, which is the generalization for of Dirac quantization to dyons. But the thing I would like to emphasize is that this formula here, actually, you know, Zwanziger managed to give a relativistic generalization of that. So he was able to sort of calculate the contribution of the electromagnetic field to the general Lorentz generators M nu rho, and now, you know, you can give it in terms of the momentum of the four vector momenta of the electric and the magnetically charged objects. Okay, and there's a curious plus minus sign here, and that's because, you know, clearly it's related to the relative direction. Yes, but if you're trying to extrapolate the position, then depending on whether you go asymptotically up or backwards, yes, you will get a different sign here. So that's the origin of that. Okay, so that's the and in a non-relativistic limit, of course, you know, you will just get the usual expression. And again, you know, the in and out states differ by a sign. And this has very far-reaching consequences. And as I said, many of the really weird properties is really following from this simple formula. The conserved angular momentum is actually different from that of the free theory. Okay, so the conserved angular momentum of the interacting magnetically charged system is different. Yes, the asymptotic states do not factorize into one particle states. It doesn't matter how far you separate them. So this additional contribution will be there, and, you know, they are simply not the product of the one particle states. Also, there is no crossing symmetry for the S matrix. Clearly, you know, it matters whether you have an electrically and magnetically charged object, or whether you have, you know, two electrically charged or two magnetically charged objects. This is going to make a difference. So many of the weird things are contained here. So what we try to understand is, you know, so how is this weird thing captured in the representation of the multi-particle states? So how is the fact that you have this angular momentum gonna show itself in the representation of the two particle states? So just a very brief recap, even though probably, at least in this audience, everybody knows this, but how do we do the classification of the one particle states? So that's something that was done, of course, by Wigner long time ago. So, you know, you start, you have a Casimir operator here, yes, so the momentum square is the same for every state in the representation. You can choose a reference momentum. For massive particles, you can just go to the rest frame of the particles. For massless particles, there is no rest frame, but you can just pick the momentum to point along the z direction. And an arbitrary momentum will just then be obtained by the boost of this reference momentum. So an arbitrary momentum that satisfies this Nash-Rod condition will be a boost of the reference momenta. And then the key ingredient, that's what allowed Wigner to find the representations, was that this combination of transformations is something that will leave the reference momentum unchanged. Okay, it's pretty clear, yes. So you take the reference momentum, this just takes the reference momentum to P. Now you do a Lorentz transformation, that's lambda P, and now you undo it, so it brings you back. So this is going to be the little group, the invariance group of the reference momentum, yes. So that means that if you take the corresponding representations of corresponding group element representations, they must be a representation of the little group. Okay, and so on the reference states, the action of the little group will just pick some particular representation, yes. And in the case for massive particles, this little group, you know, just what leaves, you know, the rest frame momentum, the one that I wrote over here, what leaves that unchanged. Yes, that's just going to be an ordinary rotation, so that's SO3, or, you know, if you're allowing fermionic states, then you can take it to SO2. For massless particles, strictly speaking, you know, there's a little subtlety here, but in practice, in most of the time, it doesn't make a difference. Strictly speaking, it's called the Euclidean group, but for practical purposes, it's essentially just a rotation around the z-axis, okay? Because you have a particular direction chosen by the momentum, okay? So, and the general form of the representation will just be, okay, so this is how the representation of the general Lorentz transformation acts in a state. So it's the representation of the little group, okay? So that's the, it's very intuitive. Basically, what Wigner is telling you, find the frame with the biggest symmetry. Yes, that symmetry is the little group. And what you're supposed to do then is, if you're not in that special frame where you have the big symmetry, then first boost in that frame, do that symmetry transformation, and then boost back. That's essentially what this whole construction is telling you. Now, what happens for multi-particle states? So we usually just say, and we assume that multi-particle states are simply just direct products of one particle states. Okay, of course, those are definitely good representations. There is nothing particularly wrong with that. But the question is that sort of the most useful, most general thing that we can think of? And it was already in 72 that Zwanziger noticed that actually for two particles, there's another special frame. Okay, whenever you have just general two particles, there's another special frame that has a bigger symmetry than the two particles separately have. Okay, and that's the center of momentum frame. Clearly, when you have two particles, you can always go into sort of the analog of the rest frame of the two particles, where the total momentum, the spatial part of the total momentum is vanishing, yes. And because there are two particles, they are just back to back in that frame. Yes? So there is an additional, just a rotational symmetry in that special frame. Okay, so that's another symmetry for a pair of particles, yes, which distinguishes, just from the individual particles. Okay, so now you can repeat the whole Wigner story for two particles, yes. So you can now have this two particle system where you have two momenta. You can choose the reference pair of momenta to be in the center of momentum frame. Yes, so you have this back-to-back momenta, and an arbitrary pair can be obtained from the boost of this reference pair. Yes, and again, the important thing is that in the center of momentum frame, there's a remaining symmetry. There is an SO2, just a U1 rotation around the axis that is chosen by the back-to-back momenta of these two particles. So this means that for a pair of particles, there's an additional little group. This is what we call the pairwise little group. Okay, and what I want to really emphasize is that this is independent from the ordinary one particle little groups. Yes, because this is something that just characterizes the fact that you have two particles. This is not something that, going into the rest frame of one particle or the other particle would take care of. It's an additional symmetry of the pair of system, yes, that appears, and you could possibly pick non-trivial representations for this pairwise little group, yes, which will then tell you that the pair of particles transform slightly differently than just the individual product of the two particles. Okay, so again, so this is independent and in addition to the single particle little groups of the two particles. Okay, so this is very clear for spinless particles, and again, you can go through this whole derivation. You can do the usual, little group story, and what you're going to find is that in principle, when you're trying to do the Lorentz transformation of a pair of particles, you could pick up an additional phase. Okay, so this is what we call the pairwise helicity of this pair of particles. That's why it's pairwise, because it makes only sense when you're talking about a pair of particles. Of course, you can choose this charge to be zero. Yes, then it's just going to be the ordinary direct product of the one particle states. But you can choose this to be non-zero also. Yes, and the most important thing for us is, what is this, this pairwise helicity? Yes, well, let's take, for example, spinless states. So do not assign spins to the individual particles, but you can do that also. Yes, and in the center of momentum frame, you can see that this actually literally gives you now a z component of the angular momentum. Yeah, so you take two spinless particles, and yet there is going to be an angular momentum here. Yes, so the important thing is that the representations of the Poincare group do have this possibility in them, and there is a physical situation that is actually calling for this Q to be non-vanishing. Yes, exactly the case when you have an electrically and magnetically charged particle, you do need to have angular momentum in the system without these particles actually necessarily carrying spin. Yes. So what you can identify is you can identify this Q, this pairwise helicity quantum number with the usual, this Schwinger product of the electric and the magnetic charges. Okay. Now I would like to emphasize that this pairwise little group is really SO2 or U1 if you're allowing fermionic states. It doesn't have that subtlety about the E2, yes, and this is SO2 even for massive particles. So we didn't use anywhere, particles being massless or anything. So this is a U1 helicity type phase even for massive particles. Now, another question that people usually ask, okay, so now how about higher little groups? Yes, I said a pair can have an SO2, yes. So now is there an analog for, instead of pairwise little group, is there a triple or quadruple little group? Well, the answer is at least not in 4 dimensions, because if you now have 3 particles, yes, and you do the same thing, if 3 momenta that add up to 0 in general don't have any symmetry left, yes. If you did go to 5 dimensions, yes, then the pairwise little group would be actually an SO3 rotation, yes, and the triple little group would be a U1. Now, I don't know any application for that, maybe somebody does, but anyway, it's a curiosity. Okay, and then again, of course, the quantization conditions you can use. Now, we also generalize this for the case of when the particles have a general spin. So this is the general transformation property for n particles. Yes, they can have their transformations under the single particle little groups, and then for each pair, you should be choosing a pairwise helicity quantum number, and then there will be this additional phase in addition to the usual one particle little group transformations. Okay, so that's the story here. So pretty simple. You can think in terms of Callan generator, but that doesn't matter. Okay, there you go. So we have this new quantity, this pairwise helicity. Now, is it useful for anything? Okay. So what we did is then we tried to actually implement this in the scattering amplitude formalism and create the corresponding spinor-helicity variable for this pairwise helicity. And in fact, we think that this is something really successful because it really allows us to rederive a lot of the results that have been known already about the scattering of monopoles from, just different kind of limits, quantum mechanical scattering, etc. So, okay, so let's just a brief review. What is the spinor-helicity variable? So, these are these square and angle brackets, yes, and basically what they do is they are objects that have the right transformation property under the little group, under the one particle little group, and they carry Lorentz spinor indices. Yes, so the definition of so this is the ordinary spinor-helicity variable. Basically, the way it is defined is that under a Lorentz transformation, it is going to pick up exactly the right phase under ordinary helicity. Yes, so this is the underlying explanation for how these scattering amplitudes are built up in the amplitude technology, in the scattering amplitude technology. Yes, so you just look at what the little group properties of the S matrix or the scattering amplitude is under the little groups of the various particles. And then you have to find a right number of the spinor-helicity variables to saturate those little group quantum numbers, and also make sure that they have the right Lorentz invariance quantity. Okay, so that's what has been done. And what we want to do is we want to do the analog of this spinor-helicity variable now for the pairwise helicity. Yes, now this is a true U1 transformation. So the expectation is that it's going to somehow correspond to a massless momentum that is made out of a pair of momenta. Okay, so we have two particles, they have their momenta. None of the particles have to be massless, yes. So each of them have their own mass. P1 squared is M1 squared, etc. But you can take a linear combination of those two momenta, and that actually can square to zero. Yes? So the easiest to understand is that we can go into a reference null momentum. So this would be something that would be corresponding to the center of momentum frame, which is essentially like a massless momentum, and then boost it to an arbitrary frame. You will see that this is now going to be a linear combination of the momentum P1 and P2 of the particles. Okay, so we call this the flat momentum because this kind of construction has been already present in the amplitude technology. People have been using these combination of momenta that square to zero when they were trying to do loop calculations. Okay, loop corrections in the amplitude language has included momenta of this sort. So we try to use the same. Notation. So then essentially once you have this concept, you can go and turn the crank and really just find the corresponding pairwise spinor-helicity variables. Yes, so there will be the corresponding angle and square brackets, and we have the explicit expressions for these. And again, the way they are defined is that under Lorentz transformations, they pick up now exactly the phase that I have defined for you in the group theory, this pairwise helicity phase. So this phase, the U1 phase, it doesn't pick up anything else, just that U1 phase, which is the U1 that corresponds to the rotation in the center of momentum frame around that special axis. Of course, it's a more complicated expression in a general frame. Okay, and so now we have these variables. Yes, so we have these pairwise helicity variables, and now you can go ahead and just try to write down S matrix elements from them. Okay, so in fact, as I will show you, it will allow us basically to fix all the angular dependencies of the magnetic scatterings, and again, there's no perturbation theory here, so that's pretty nice. So that's one of the reasons why I really like this as an application of amplitudes. Because amplitudes, of course, can rederive a lot of the things that people can do using Feynman diagrams, and in many cases they can derive things that is technically not possible, but with Feynman diagrams, at least in principle. But here, this is an example where it's not quite clear how you would do it, using Feynman rules. So let's just give you an example here. Okay, so let's do the decay of a massive fermion into a massive fermion and the scalar. Yeah, so there's a spin 1/2 particle in the initial state, spin 1 in the final state, and we are assuming that the initial particle was a dion that decayed, and one of the particles is carrying the electric charge, the other one is carrying magnetic charge. So there will be pairwise helicity in the final state. So we just assume that it's 1. Okay, so in the units when 1/2 would be the smallest one. So in that case, you need 2 of these pairwise helicity spinners, and then you need 1 spinor for each of these fermions. So this would be sort of the form of the scattering amplitude that you can write down. Okay, so then we were able to sort of do this in general for the decay of an arbitrary spin 1 particle to spin 2 plus spin 3 with arbitrary electric and magnetic charges. So you can you just count how many ordinary spinners you need, and then you have to saturate their spinorial quantum numbers with the pairwise spinor-helicity variables that you have to add, and you also know how many of those you have to add because you know the pairwise helicity of the final state. So you get some nice selection rules that is telling you that this pairwise helicity, which is the E times G, cannot be too large. It cannot be bigger than the sum of all the spins. Otherwise, all the scattering amplitudes are going to be vanishing. So we have a general formula for this. then I'm running out of time, so I will just quickly outline what happens in 2-to-2 scattering. So here, the kinematics will not be, so this is essentially kinematics, what we are doing here, yes, there's no dynamics included. Yes, it will not be enough to fully fix the S matrix, but it will be enough essentially to fix the angular dependence in the partial wave decomposition of the scattering amplitudes. And it turns out that there will be only phase shifts that are undetermined for each partial wave. And we can go back, for example, and cheat a little bit and pick those out from the quantum mechanical calculation, or and the lowest partial wave will be completely fixed. So that's something that is very famous from the 70s, that was done by Kazama, Yang, and Goldhaber. And it turns out that you only have a helicity flip amplitude for the lowest partial wave. That's sort of the analog of the Rubakov-Callan helicity flip that for the simplified case, and that follows very easily from our formalism. And in the higher partial waves, we are able to identify the so-called monopole spherical harmonics that naturally appeared in the quantum mechanical calculation of scattering from Wu and Yang. So maybe I'm going to skip here the description. Just one thing that you can write the angular momentum in terms of the spinor-helicity variables without pairwise. It's just the sum of the ordinary spinor-helicity variables, and there's a very simple generalization in terms of this pairwise stuff. So we use this, and I'm not going to talk about this. There are analogs of the Wigner-Eckart theorem. There are essentially Clebsch's, and then there are some matrix, some reduced matrix elements. And again, we do find the helicity flip and non-flip amplitudes. And I'm not going to say more about this. Let me just say a few words about the scattering of gut monopoles. That's of course, one real life problem. Yes. So, the gut monopole is of course the thing that is embedded over here. Yes. So this is SU5 broken to 3-to-1. The gut monopole is coming from the breaking of this SU2 subgroup. Yes, that's the one that is broken to U1, then SU5 is broken to 3-to-1. You can count, how the standard model fermions decompose under this. It's going to be 4 doublets. Everything else is singlet under this. So there should be an SU4 symmetry here. And so you can try to ask the question, what are the various scattering amplitudes when you scatter, for example, a proton on a monopole? So that's the very famous Rubakov-Callan amplitude. And of course, very sad that Valerie just died last week. That's was a real bummer. And what we did is we were able to, take the scattering amplitudes corresponding to this Rubakov-Callan case and find, again, the fact that there has to be, that there's no forward scattering told you, that there's only a weird baryon number violating operator that is present. And we were able to identify what the only possible final state is, which is helicity flipping. All quantum numbers are conserved, and this is the only amplitude. So because unitarity has to be saturated, this one will be unsuppressed, and that's the one that is giving rise to baryon number violation. Okay, now there's another puzzle that is related to this story, which is Callan's unitarity puzzle. What if you scatter a positron on the monopole and not a proton? Then you can check what the allowed final states are. So this is the only possible allowed final state. But it turns out that if you write the most trivial contractions of these spinors, this is actually 0. Okay, so this was, this caused sort of a big upheaval. People didn't know what the possible final state is, and Callan truncated the theory. There's a lot of work going on to find what the answer is. So in this truncated theory, it looks like there are some fractional fermions that are showing up in the final state, and the quantum numbers are only statistically conserved. Now, in our formalism, actually, we can identify a possible final state with whose contraction on these amplitudes is non-vanishing, this one here. But you see, the key is to the contraction of one of the quarks with not its corresponding pairwise helicity spinor. Okay, so this amplitude satisfies all the this amplitude satisfies all the all the conservation laws. It is a total J equals 0 state. It is baryon number violating as usual. There is no fraction of fermions. However, we are not sure that this is the right solution, yes, because we don't have a dynamical explanation for this. And the one thing that we don't have is that if you look at the pairing of these states, yes, they are now not going to be all in the J equals 0 state pairwise with the monopole. It's the total J equals 0 state, but it's not J equals 0 pairwise. So, of course, we don't really know if the whole quantum mechanical scattering amplitude is going to factorize into the scattering amplitude of just one particles on the monopole. If it does, then this is probably not the right answer, yes, because then probably this is exponentially suppressed. But we don't really know. So this is a dynamical question. I wouldn't, I'm not taking any side here. All I'm saying is there is a non-vanishing amplitude that we can identify. This could possibly be the right thing. And let me just take one more minute. Until now, all I told you is group theory and application of group theory. Is there a dynamics behind this pairwise helicity? And of course, the reason for this unusual behavior that I started out with is that you have very soft photons, and the very soft photons can be exchanged over very large distances. The interaction doesn't die out. Yes, so this is a typical example. Then our perturbation theory, the way we are organizing in the interaction picture, is not quite correct. Yes, because the asymptotic interactions don't die out. And this is a well-known situation that was already looked at by Faddeev and Kulish, who were trying to understand the infrared divergences in QED. Yes, and what they found is that actually what you're supposed to do is modify perturbation theory. Yes, well, you are making a mistake. You know that you are making a mistake because the interaction doesn't go to 0. So let's just take the asymptotic part of the interaction potential and define it to be part of the state. That should be your dressed state, which includes the effect of these very soft photons. And what we found is that if you do that, then all the IR divergences in QED go to 0. So let me just, since I'm out of time, let me just say that we repeated this procedure. Of course, it's a little non-trivial because we needed a Lagrangian for this. So we picked this two potential Lagrangian from Zwanziger, and we repeated this procedure, and we did in fact find that these dressed states, these Faddeev-Kulish dressed states, will have exactly the transformation properties that you are expecting from the group theory. So we could identify exactly what the origin of this additional phase is. And again, it's coming from the fact that this contains the soft photons. Okay, so let me not do this. And in this formalism, we actually are also able to sort of identify a purely quantum field theoretic derivation of the Dirac quantization. So we don't need to do Aharonov-Bohm. So it's really quantum field theoretic. There will be a Berry phase showing up here, and we can derive the Dirac quantization. Okay, so again, pairwise little group is really cool. It's probably will have a lot of applications whenever magnetically charged objects are present. It's the key ingredient into solving this scattering of magnetically charged objects. We were able to identify this new building block for the amplitudology, which is the pairwise spinor-helicity variable. We were able to construct the 3-point functions, fix the angular dependence of 2 to 2, had the helicity flip, the monopole harmonics, the Rubakov-Callan scattering, and possibly a new solution to the semiton puzzle, and the dynamical origin. Distressed states as a Faddeev-Kulish state is what is the origin of this. So let me end with this, with another nice picture of Hiroshi and Aspen, and wish you happy birthday.
So we're running very late this one.
Okay, thank you very much, and thank you very for the very next talk. So maybe I was just misunderstood what you said. But so in 4-dimensional case, you have this pairwise representations, and then but no triple or
exactly.
But in higher dimension, you said there are
There would be triple, there would be,
What kind of situation do you have in mind? Because, for example, a magnetic dual would be like strings or membranes.
right, so, okay, so that's good. So here I was talking just about 5-dimensional particles, yes? So 5-dimensional, brains, there is a way of generalizing pairwise helicity to brains. So that's actually something that we are in the process of considering. So there, of course, this pairwise helicity is going to show up not between two brains of the same dimension, yes, but you have to have a p brain and a d minus 4 minus, I forgot exactly what brain. They will have a non-trivial pairwise helicity.
But that can also be tripled and higher.
That's a good question.
Yeah, because I found it like this because at least when the interactions are linear,
Yes.
then the kind of contribution to the momentum is always
Right.
because you have charge.
Right. So that's a good question. I do not know the answer, and in fact, right now we are stuck at the point of trying to understand just. Okay, we know in which situation there will be a non-trivial pairwise helicity for brains, but we are going back to ask the question. So, but exactly how does the brain represent the Poincare group? So maybe some of you can help me because exactly how does the little group of just a single brain, come out of the Poincare group? I would like to, that's where we are right now. Yes. All right. Thank you very much.